Okay, geometry week 10. Oh my, is it the last week of the second quarter? I guess maybe it is. So we are going to start quadrilaterals and IXL N 1 through 6. Let's make sure we all know what that is. All right, so hopefully you finished all of R. And so we're going to look at N. So go ahead and go there with me right now. IXL N 1 through 6. Quadrilaterals. So the way I'm going to start doing IXL the second half of the year is it's not going to be with what we're practicing, but it will work to overall as a whole. So, we got the whole quadrilateral unit here, 1 through 14 in IXL, and then we have our textbook. In our textbook, we're going to start out with parallelograms. And so we have that. I don't know why it's not loading here. But in IXL, we're going to start out with trapezoids. But I think you can handle identifying when you have a trapezoid. And then, by the end of it, it will all come together. Okay, so whatever issues you have, just make sure you post in the organizer. Let me pause this video, get this loaded up. All right, move closer to the router. So let's get started with quadrilaterals and polygons. So we always start quadrilaterals with the angles and polygon. Now, this is probably shouldn't be brand new information, but if it is, we're going to start here, so that's okay. Diagonals are from a vertex. So the vertex and polygons are the capital letters, the points, the corners. And then a diagonal is a line that you can draw, straight line in the polygon, that is not a side, but it goes from one vertex to the other. So you have your sides, which is from vertex to vertex that makes the polygon. And then you have your diagonals, which are drawn in the interior of the polygon. And why do we care about that? Well, we can actually come up with a little polygon interior angle sum theorem based on those diagonals. So a triangle has no diagonals, and we know it's 180 degrees. A quadrilateral has, well, you might say it has 2 diagonals, right? But if you draw a second one, it would intersect with the first one. So if we draw non-intersecting diagonals, they don't intersect in the interior. There's only one, and so that gives us 2 triangles. And a quadrilateral has an interior angle sum of 360, which is 180 plus 180. And a pentagon, you can create 3 triangles. So that would be 540. Hexagon, 4 triangles, which is 720, you see here. And we end up with our little theorem. 2 less than the total number of sides times 180 is the interior angle sum of any polygon. Pretty cool. And then, so let's do guided practice. Find the sum of the measures of the interior angles of a convex octagon. Oh yes, it has to be convex. So let's just put that in our notes. Convex, and the opposite, I'll put over on the opposite side, concave. Convex means that, well, there's a formal definition, but the definition in my own words that I'm just going to say is there's no dent, doesn't go in here. See, a concave, I always say, has a cave. So you see, you can draw a little caveman. It's concave. And then if you can't, it's convex. Okay, so we'll go with that for now. So the sum of the interior measures of a convex octagon. So Octagon has 8 sides. Make sure you know your gons. We have a triangle or a trigon, a quadrilateral. I don't know, call that a fourgon or something. Pentagon, hexagon, heptagon, octagon, nonagon, decagon, and 11gon. We don't. So if you don't know the name, you can just put the number in front of the word gon, and gon means side. And a dodecagon is a 12. Okay, so if we have 8 sides, so that means n equals 8. So 8 minus 2. I'm going to try to speed this up a little bit. So 6 times 180. What is 6 times 180? 6 times 180 is 1080. There we go. 1080. So that's the sum. Find the measures of the interior angle of a pentagon. So we know a pentagon is 540, right? From the table above. And so we could just set up the equation 2x plus 142 plus 2x plus 3x plus 14 plus 3x plus 14 equals 540. You know, or I had a student one year that just adds up all the x's together before they write the equation, which I always thought was better once I saw them do that. So 3 and 3 is 6, 8, 9, 10. So we can just write 10x plus 142 plus 14 is 156 plus 14 is 170, unless I messed it up, equals 540. And so you could solve that. Okay. So what is this one? Interior, okay, real life. Coins. Find the measure of each interior angle of a regular pentagon that appears on the face of a Susan B. Anthony $1 coin. What in the world is a pentagon? Let's all look that one up together. Pentagon. Oh my goodness. A pentagon is a 11. Oh, so it does have a name. This is the first time hearing of this. A pentagon is an 11-sided figure. So for this one, what we're going to do is, so we want to find the measure of each interior angle. So you just have to do one more step. You have to divide by 11. You know, so it's going to be 9/11 times 180. Well, let's figure out what that is. 9/11 times 180. 147.27. So that's the answer. 147.27 degrees. Each angle in a Susan B. Anthony. Hot tubs. Find the measure of each interior angle of a nonagon. So you can do the same thing with 9 sides. So it's going to be 7/9 times 180. Okay, you can do that one. The measure of an interior angle of a regular polygon. Oh, write this down. New vocab word. Regular means all sides and angles. All sides congruent, all angles congruent. Of course, the sides are not congruent to the angles, but all the sides are the same. Separately, all the angles are the same. And so it's 144. Find the number of sides, and we can just work backwards. We know our formula is n minus 2. And now we can say divided by n times 180. They're telling us equals 144. All right. So we can put this 180 on top, and we can make this into a fraction. Because, you know, Mr. Field likes cross multiplications. And it'd be 180 n minus 2 all over n equals 144 over 1, and then just cross multiply, equals 180 n minus 2, and distribute, and you can take it from there. Dot, dot, dot. Y'all are geometry students. Okay. So we not only have an interior, we also have an exterior sum, and you will prove that in exercise 43 and probably on the quiz as well. The sum of the exterior angle measures is always 360. Isn't that amazing? So as the interior angles get bigger and their sum gets bigger, the exterior angles shrink. And so just to draw a little picture of what that looks like. So you're like, what? This is crazy that it would always be 360. So here's a equilateral triangle, and we know that all of those angles are 60, which makes all the exterior angles 120. And what's 120 times 3? It's 360. And then here, let's draw. It doesn't have to be a regular polygon, but just to make a simple illustration. See how the exterior angles got smaller when I made it into a square? And what's 90 times 4? 360. And so a pentagon, well, and you know, they get smaller, I think they're 60 or something, and so on. So it's always 360. So you can set up an equation for that one too. Find the value of x in the diagram. No problem, textbook. So I'm just going to add all these together and set them equal to 360 because I know that the sum is 360. So 6 and 2 is 8, 17x plus 139 equals 360, and you can solve that. Find the measure of each exterior angle. Well, you can do that. Just divide it by 360. Okay. Now let's do one more section. Start out our parallelograms. Okay, so parallelograms are the first quadrilateral, and we will do the quadrilateral family diagram in class or maybe in the next video here. Maybe should we? Yeah, but right now let's start out with write down these properties of parallelograms. And there's going to be properties and for each quadrilateral it will have a definition, and we know that definitions are important. Okay, so some things, you know, so some things share properties, but each figure has a specific, so these can be shared. For example, what is true in a square and a rectangle? What is true in both of them is that they both have opposite congruent sides. They both have opposite parallel sides, which is also true in a parallelogram. You know, the square and the rectangle have 90-degree angles, not the parallelogram. So that these properties that some exist in more than one shape, but a definition is something that is specific to the shape. And so if something has the definition, then it is that thing. All right. And so that's why we always know that a square is a rectangle, because it fits the definition of a rectangle. But a rectangle is not always a square. Okay, so these are specific, and if a definition is shared, then you say, oh, it is that thing. But a property can be shared and it still not be that thing. Okay, so we have our opposite sides are congruent, opposite angles are congruent, consecutive angles, that's consecutive means like in a row, like those are consecutive, these are consecutive, these are consecutive, and These are consecutive. All right, so they are supplementary, and if a parallelogram has one right angle, then it has 4. And guess what? We're going to be doing a little bit of proofs in this chapter, but not as many as when we did triangles. All right, so let's look at these properties, and a lot of it will be algebra, won't be bad. The wall-mounted mirror shown uses parallelograms that change shape as the arm is extended. In parallelogram JKLM, suppose measure of angle J is 47. So put a 47 in there. Find each measure. So if we know if this is 47, then this is 47. And then we know they add to 360. So then we could just take in, why not? 47 times 2 is 94. So then we got the 360 minus 94. So the other two angles add to 266. And if you divide by 2, they're 133 each. So these angles are 133. All right, so L is 47, M is 133. Not too hard, didn't even have to write out the equation. Suppose the arm was extended so that angle J was now 90. What would be the measure? So we know that the last property said they would all be 90. And it says justify your answer. That means give your reason. And it's just like a proof, right? So I'm going to write theorem 6.6. If you can't remember that it was theorem 6.6, you could just write down what it said in that theorem, which would be if there's one right angle, there's 4. That's a theorem. 6.7, 6.8. All right. The diagonals bisect each other. That means that where they intersect is the midpoint of both of them. So this is congruent to this, and this is congruent to this. That's what that means. And if a quadrilateral is a parallelogram, then the diagonals separate it into 2 congruent triangles. So this triangle is congruent to that triangle. Lots of little theorems that happen just because we have a parallelogram. So right here, we can solve for x and y. We can solve for x because we know that consecutive angles are supplementary. So 4x plus 2x minus 6 equals 180. You can do that. And then we also know that opposite sides, if you look back, or you should have written it down, are congruent. So we can also solve y plus 8 equals 5y. Opposite sides congruent. And I'm going to write my justification. Consecutive angles are subs. And at this point in geometry, I do want you to write down your justification in parentheses next to the equation that you set up. Because as you can see, lots of things add to 180 and lots of things are equal to each other. So you could just guess and get it right. But if you justify your answer, I'll know you're not guessing. Find the value, and then here we know that the diagonals bisect each other, of course, which means we can set them equal. And so we would set that equal. So you guys can solve this. I'm just writing it and trying to make a shorter video because I talk a lot. Diagonals bisect. Diagonals bisect. And coordinate geometry. Okay, so we'll stop here. We'll do examples 1 and 2, and we'll pick up with coordinate geometry and proofs next week because I think this is enough for us to do this week. Have fun.